Okay, welcome back to part 3. So we move on with derivative. Now derivative is the rate of change. I think this rate of change idea is always a bit confusing for students. A rate of change is, there are a couple of things. It's a number. And then what does that number mean? That's a really good question. So what I do is generally get some students to line up with me and we go for a race. Not a proper race, but just a adjacent race. Here I am there. And I might go along at 1, 2, 1 meters per second. That's my rate. And then somebody who's a bit healthier than me, a bit younger, a bit fitter, go at 1.5 meters per second. That's their number. Someone might go along at 3 meters per second. Someone might go along at 5 meters per second. Well, that's certainly pretty quick, isn't it? But the idea is it's just a number. I think we get caught up because of the units. I think students get confused by units. But it's just a number. So we could extend that. We could extend that to a bike or a skateboard. We could put a bike together. What about a car? And so you could work it out, couldn't you? You could work out a train. Train tracks. What goes faster than a train? A plane. Okay, what would the plane, train, car number be? Maybe 5. Go a bit faster, couldn't it? Maybe double. Bike could go a bit more again. Certainly a car could go 40. What about a train? They seem to be able to go 100, don't they? I know it's an exaggeration. What about this one? 1,000? No, I don't think that's quite. Kilometre a second, maybe. That's pretty fast. Pretty bit too fast, probably. But we can convert all those to kilometres and work it out. But the idea is it's a number. Okay? So these ideas are pretty simple. A rate of change. It helps to inform about in the model of a physical system. So when we get to a rate of change, we don't want to be too upset by it. All right. So the idea of the derivative is it can be interpreted as an instantaneous rate or an instantaneous moment in time. That's what the tangent is. The tangent gives us an instantaneous moment in time. Okay, and the rise over the run of that tangent is the whole thing. Okay, the rise over the run at that instantaneous point in time. So that's that instantaneous rate of change. Okay, so we move from being averages to what's happening at that moment X or at that moment T, whatever it may be. Okay, so when X approaches some A, so we say that X approaches some value A, we would do that with that kind of nomenclature. All right, so the little delta X is the difference between, in other words, it's the distance between X and A. What's the distance between X and A? So the smaller delta X, the smaller the distance. And we can make that we can be absurd here and make them incredibly small, almost so you can't see them. Okay, but out of here is a distance. What's the distance? It's infinitesimally small is the phrase that we would use. Okay, infinitesimally small. Infinitesimally small as X approaches A. That's what we want that delta X to be. So then the difference between the functions becomes the function value. If they're very small, they'll be very small. So that gives rise to the idea. And so the rate of change is just m again, so don't lose sight of that. But we're expressing it in terms of the function value, y, because it's the rise. And we're expressing it in terms of x, y, because it's the run. So that hasn't changed. And so we get this kind of value as the difference, as A approaches X, Okay, we get this kind of instantaneous rate. So this is the average. The instantaneous one is the one where we have our insurance policy, because we can't let that become zero, that denominator, can we? So as soon as we bring in the insurance policy, what we're saying is, hey man, what's going on here? This becomes the derivative. It's all very complicated in that way. All right, so we don't want to linger too deeply at this point. There's simply not the time that we need, really, to go through all of the bits and pieces that we need. So what we do know is that once we establish a particular rate of change at a particular time, that there's going to be a tangent. And look what the tangent has. The tangent has a linear value, y equals mx plus b. So the tangent is a straight line. And all of these things are here contributing to this. Okay? The increment, infinitesimally small changes. Okay? So they give us the idea of a gradient. So it's quite a straightforward idea. All right. So we now come to the doing. So the doing of this. The doing of this is fairly straightforward, isn't it? We've been doing code 1, code 2, and all of that kind of thing. So for all the different rules that we'll have, I think the thing that we're most interested in is probably the chain rule, but we're not quite there yet. So for this one here, here's our derivative, or M curve, gradient, M curve, gradient. What else are we going to call it? Rate. So any number of things that we can call it. So for the example here, y is equal to x squared. So the derivative will be equal to, bring the 2 out the front, take 1 off the 2, 2 minus 1 is 1, which is 2x. So we start off with a y dash, it's 2x, and y is x squared. So we've got the original function and its derivative. Okay? Its original function and its derivative. So we know about y equals x, don't we? The gradient m, y equals mx plus b, to 1. We know that just from our geometric interpretation, because you move your elbows and your arms, don't you? You set it to 1. So that's the simplest one. Strictly speaking, that's a function, not a rule. But we'll set that aside. Now, what about these constants? What happens with the constants? Are they there as well? Well, I guess we could think about it as y is equal to 6x squared. What would that be? Well, the derivative would be, the 2 would come down and multiply by the original form, and 2 minus 1 would be 1. Now look, that's still there. It's there as 12x. So it's still there, the constant's still there. So anytime there's a constant, it remains. The 6 is still there, it's just been absorbed in a sense in the multiplication, but it's still there. 6 is still here in your maths eye. Alright, so there's a few of them that we can look at. Anything that's a constant has got a gradient of 0, so that's just putting your elbow and your arm down flat. And then, of course, we've got composite parts, which means if there's a polynomial, you can do it step by step. So this is an example of a polynomial. We can consider this f of x, g of x, h of x, j of x. We can consider all of these functions as piecemeal functions, okay? And all you do is differentiate term by term. That's what this means, differentiate term by term. So we've got our rule, the one that we've been doing from first principles and from code 1 and all the rest of it that we've looked at. So what about the differential? Well, the 5 comes out the front and multiplies by the 4, so that's 20. You take 1 off the 5 and so that's 4. Don't forget the other terms. 2 comes out the front, multiplies by minus 12. Be careful. 24x. 2 becomes a 1. I'm not even going to write it. 2x has got a 1 there. The 1 comes out the front, multiplies by the 2. And then you get x to the power 0, which is 1. So 2x becomes 2, and the constant's gone. The constant is 0, so I'm not going to add plus 0. Okay? For these guys here, we've got a little bit of pre-work to do. A little bit of pre-work. So y is equal to x to the half. I say. Okay, so that means the derivative is going to be equal to, bring the half out the front, x to the half, take 1 off. So now I'm writing the steps. I have been forced to because of the fraction. Okay, so take this up, half minus 1. I know you know it's minus a half, but we'll just do it for the sake of humour. 1 minus 2 is minus a half. So we've got a half x to the minus a half. I'll do this once the long way. 1 over 2x to the half. The fractional indice means the minus is gone. The fractional indice means the radical. There you go. So that's our final derivative, y dash. So you can see here what's happening. The bit that we did the calculus on, put the half out the front and take 1 off, 2 seconds. We seem to be going on with this forever. Calculus is not the problem. Okay? Calculus is not the problem. All right, a bit of pre-work here. Let's see if we can do some pre-work. I've got y is equal to x, which has got the denominator of 3 because it's a cube root, and the 2 sits on top. So now we're ready to go. I wonder what the problem will be. Let's do the calculus. Are you ready? 1, 2, 3, 4. Done. There it is. We put the number out the front and subtracted 1. Done. Oh, that was only 4 seconds. It took more effort to work that out, I think. The pre-work. What about this then? 2/3 minus 1. Oh dear. So we get 2/3 x to the minus a third cube root down. So it's going to be 2 over 3 cube root. 3 goes in there. X to the power 1. So that's our final derivative. Okay, calculus is not the problem. It's all about indices and gymnastics and other adding fractions and the like. So a bit of pre-work here. Let's pull this up. So y is equal to x to the minus 1. So now we can go ahead and differentiate. Y dash will be equal to minus 1 comes out the front. Minus 1 minus 1. So we get minus 1 x minus 2. That means we get minus 1 over x squared. Okay, and that's our gradient function, our m curve, our y dx, our y dash. Okay, so these are quite important ideas in the first instance of being able to develop your sense of doing lots and lots of examples. Okay, so Pearson's there for you to do your practice in that regard. All right. Now, I'm going to do something a little bit strange. I'm going to have a look at this product rule and quotient rule in this video because I want to emphasize the chain rule. I'm happy to do the product rule, but all right, so what is the product rule? The product rule is when we have a product in X. Now, it can't be a number. That's not a product rule. Okay, a product rule is when you have something like the ln of X times e to the X. Now, that's not an undo. That's just a product. So you have to be very careful how you interpret these. In this case here, we've got linear factors, and so we're going to explore those as part of the rule. Now, this is the first time you assign a variable. And in fact, what you do is you assign 2 variables. Now, these 2 variables are going to help us unpack the product rule for differentiation. Now, I'm going to use u and v. There they are, u and v being used. But there are others. You can use m and n. mean P and Q and R. As long as you keep track of them, it's okay. Okay, you could use W, U, V, W, VW. I'm not sure about X because it's usually a function value, an independent variable. So we can choose those. All right. So in terms of the product rule, if I had a priority like a list, what I'm going to do, and so on and so forth, I'm going to make the chain rule number 1. The product rule I'm going to put at about 4, really, and that one at 7. So you will encounter them, these 1, 4, and 7, but the one that I want to emphasise, the one that I believe you need, the maths one, is going to be the chain rule. So let's do a product rule in any case. So we assign to U, and that's a V. It's a V because of the top bit. We assign to U x cubed plus 2. Now I could write that out, couldn't I? U equals x3 plus 2. And then I could write out du dx or just u dash. Very bad habit. What would that be? 3 comes out the front. 3 minus 1 is 2. The 2 is a number, so it's a constant. It has a gradient of 0. V, on the other hand, is equal to 3 minus 2x. So V dash is equal to negative 2. Okay? So you can use those 4 pieces of information now and recognise that y dash, there it is. I'm going to put it in slightly different form. U dv plus v du. Now what's the difference? Not much, other than I put that term first and that term second. Now why did I do that? Because it does happen. Convention does happen that way. The reason that this is done in this order is, and they're teaching this in schools now, is because this is a match for that. All you've got to do is change the minus sign. So if you write it down as u dash v plus v dash u, I said u dv plus v du as a bit of a song, and we can put them in. So y dash is equal to this. All right, so let's put it together. x3 plus 2 and minus 2. V is 3 minus 2x, and u dash is 3x squared. So this is going to make a minus. Okay, so we're going to get minus 2x cubed minus 4 plus 3 3s are 9x squared minus 6x cubed. Okay, so minus 6x cubed minus 2 is minus 8x cubed. So they're done. Plus 9x squared minus 4. So that becomes our y dash. Alright, so the use of the product rule is fairly straightforward. You get your 4 parts and you substitute them into the rule. Now, if I did it that way, it would come out exactly the same thing. I'll let you do that. Alright. U and V. So U dash will be equal to 2. V dash will be equal to minus 6x5. Just following the single rules, just doing them one at a time. So Y dash will be equal to U dv plus v du. But it's also equal to, let's bring this one down, U dash V plus V dash U. So it's just the swapping of the terms, that's all. Doesn't matter which way you do it. Does not matter. Okay, so we get 2x5 times V dash, so I'm going to put the V dash first. And U is 2x minus 25. V is that one, and U is 2, so we'll do plus 2 times 1. because we're just used to working on the left. Okay, now we've got to expand them. Taking care. So minus 12x 6. Minus times minus is a plus. Now 25 times 6 is 4 25s are 100, so it's 150. x5 plus 2 minus 12, minus 2 x squared. I'll erase that. Minus 2x squared. Minus 2 plus 2 minus 2x6. Okay, so minus 2x6 minus another one is minus 14x6 plus 150x plus 2. And there's your final answer. Okay, now over here it's the same thing, we're just putting them in different orders. Okay, so this pair are going first. It's not actually changing anything. No, not changing anything at all. Okay, so you'll end up with the same thing here. Alright, so what I'll do there is that's the quotient rule. So we've got some, that's the product rule, so we've got some quotient rules to come up. And I'll do that in the next video. Back soon.